All right, time up. Time's up, time's up, time's up. Now, I had a great question that nobody's ever asked me before. And I think it's a function of Mary having worn a cast for like 3 months. When you use these right-hand rules, you point your thumb out, right? You don't bend it back over your palm. You got to point it out, right? Nobody's ever tried to do that before. All right, so this one. The magnetic field points west, so I'm going to use my map again, where west is to the left of the piece of paper. The charge moves south, that's towards the bottom of the piece of paper, and yet again, my palm points down into the paper, which means the charge will be forced down into the ground. All right, magnetic field points up. My hand points up. The velocity of the charge is down. My thumb doesn't do that. But that's fine that my thumb doesn't do that, because there's no component of this velocity that's perpendicular to that. So there is no force whatsoever. So if your thumb can't do what it's supposed to do, then that's a very good indication that you better make sure that there's a component that's perpendicular. There's not. There is no force whatsoever on that charge due to the magnetic field. All right, magnetic field north. That's towards the top of my piece of paper. Velocity of the charge is west, so that has my palm pointing down. But it's a negative charge. So a negative charge will be opposite a positive charge. So even though my palm points into the ground, the negative charge will act the opposite way, so it will be forced up into the sky, directly up into the sky. All right, and then finally, magnetic field is north. I'm just going to use my piece of paper again. Because if I'm in the media center and I don't know which way north is, I'm going to start going nuts, so let me use my map. So my hand points towards the top of my piece of paper, and then the velocity of the charge is northwest, right? So that could be anywhere in between towards the top of my paper and towards the left of my paper. It doesn't matter. Anywhere that I put my thumb, my palm still points down into the paper, which means that charge gets forced down into the ground. Other questions on using this second right-hand rule to determine the direction of the force on a charge moving through an existing magnetic field? Ethan.
Oh, we were just discussing northwest isn't perpendicular.
Northwest has a component that is perpendicular to north. Yes. And that component is west. It's not east, it's west. So that would be a weaker force than if it was going perfectly west, but it will still get forced down. Yeah, Patrick.
For the negative charges, can you just use your left hand?
Yes, you could use your left hand. You would always get the correct answer. I don't want to do that. You will not see me do that, but if that clicks with you and you're going to remember to do that in May of 2015, fine. Miles.
Let's say the magnetic field is pointing north,
yes,
and the charge is moving like southeast. Are you trying to like get your hand all the way over here, or can you not do that?
Well, you can just point your thumb east, because that's the component of the velocity that's perpendicular. So my thumb can go southeast. My thumb can bend about, I don't know, 110, 115 degrees.
Or you can just turn your thumb or your whole hand in the...
You can either, well, you can't turn your hand, because your hand has to point.
Like this.
So give your example again.
I don't know, I'm not
Let me do it. Well, fine, then I'll do it for you. So the magnetic field points north, and the charge is moving southwest. All right? So my thumb, I'm going to turn my map like up this way. My hand points to the north. My hand has to keep pointing to the north, regardless of what I do with my thumb. And then how do I get southeast? Well, here's east. That's a little tiny bit southeast, right? My thumb is pointing down a little bit, and that's fine, right? That's fine. Whatever. It's pointing southeast. My palm's pointing up towards the sky, right? If I can't get it enough southeast, then I just need to point my thumb east, because that's the component that's perpendicular. All right, so what do I want to do? I actually do have a tiny bit more I want to say about this, but I'm okay if we don't do that today. So what I'd like to do now is transition to review of topics 1, 2, and 3. Let's point out a couple of additional things about the makeup of your exam. Now, IB, as you guys know, IB tells me how many hours it should take for us to cover each topic, right? So I calculated a percent of each topic for just the first 6 topics. And when I wrote this exam, I couldn't do this exactly, but I tried to somewhat do this. So roughly 9% of the marks should be from topic 1, roughly 32% of the marks should be from topic 2, right? And then the rest of them are roughly equal to between 13 and 19%. So don't ignore topic 2. Roughly a third of your exam should come from topic 2. I do want to skip my topical review for a moment to just talk about logistics, and then we'll go back and do the topical review. That's not it. Alright. So the most important thing is when and where. So this is the very first midterm that you're taking. So that's 8:30 to 10:30 on Monday. You are all in the media center. I am expecting to get into the media center early and distribute Scantrons that have your name on them. So, hopefully it'll be just like our regular tests where you walk in and find your name. Okay, but you shouldn't bring your backpack or your stuff with you. So your proctor, will tell you where that stuff can go. You're going to use your own calculators. I don't want graphing calculators though. Yeah, I know you can still program non-graphing calculators, but I think it's a whole lot harder. So non-graphing calculators only, borrow them from siblings, borrow them from friends on your swim team, whatever. And then no other electronic devices besides the calculator. Don't have your phone on you, no Kindles, Nooks, iPods, whatever. Don't put me or the proctor in a situation where we have to tell Dr. Reno that your phone is making noise during the exam. It's going to be quiet enough that we hear vibrating, right? What else? It's fine with me if you have a non-sciencey or mathy book under your seat in the event that you finish early. Hopefully you will finish early. Questions about, I have some more logistics, but questions about that stuff before I move to the second page. Yes?
If we don't have a non-graphing calculator, could we borrow one from you or?
Theoretically, I have enough, but we're going to have, there's 38 of you, which is only about 24 seniors, that's 52, there's about 80, it's 130 something of you taking a physics exam at the same time. It is probable that I would have enough to give to people that don't have one, but I promise you that will not be a priority of mine. So that would be like absolute last ditch effort would be getting one for me. Alright, the only other things I could think of is, I have no idea if there's a functioning pencil sharpener in the media center. Even if there is, you don't want to have to waste testing time to wait for Patrick to sharpen his pencils. So pretend there's not going to be a pencil sharpener. Be ready when you walk in the room and get there quicker. You're not going to be allowed to leave your seat until 10:30, so don't even ask. I don't want you to poop your pants, so if you seriously have an emergency, you're going to go, but don't expect to come back and keep taking your midterm. Either you're getting zeros for anything you haven't done, or you're taking an ultra hard makeup midterm. And then the very, very, very last page of your exam, really the back of the last page is blank. So if you do run out of room somewhere on the paper too, that's where you should continue. But make sure that you make it very clear in the space for that problem that I need to look there to find some of your work. What else? What am I forgetting? What do you still have questions about in terms of logistics or anything for Monday? Brian?
Is it the 30% for the multiple choice?
40% paper 1, 60% paper 2. And remember, and I think I already gave you this, there's 17 multiple choice questions, right? There's 3 big paper 2 questions, but you choose one of those 3 big paper 2 questions to answer. Don't make me choose. Don't make me choose. If things are going well and my grading's going easily and I get all my labs graded, then I'll pick the one that looks like it's most complete. But if I'm rushing, I'm going to pick whichever one looks like you've answered less of to save myself time. Right? Don't make me pick. Don't make me pick. You pick. X out the ones you don't want me to grade. All right. So we got 3 topics to go through today. You're back. All right. So in topic 1, there's a lot of stuff there. It's the smallest percent of our exam, but there actually was a lot of stuff. I am just picking out the things that I thought were worth mentioning because they're ultra important or easily forgettable. So one of the things in topic 1 was knowing 6 of the 7 fundamental SI units, right? Candelas we don't need to worry about. But what's the one up here that's kind of hardest to logically come up with yourself? Amperes, right? Amperes, right? That's the one that's not a given. In fact, it's a little bit illogical. It seems like the Coulomb ought to be the fundamental unit, but it's amperes. The other ones, I think, are easier to come up with. What's that? What?
Well, it uses coulombs per second.
Correct.
Yeah, it doesn't make any sense.
Well, it does, it should be starting to make sense now that we're talking about wires creating a magnetic field, and then charges feeling a force because of existing magnetic fields. It should be starting to make sense that we base the fundamental unit for electricity on that. All right, also in topic 1, we talked about random and systematic error. Sometimes there are questions about, looking at a graph, maybe seeing that there's an apparent y-intercept when we think there shouldn't be. That would be a pretty good indication that there's a systematic error. We want to remember that the only way to reduce random error, once we've established our procedure, is to do extra trials. So we want to remember the distinction between those. We had a lot of dealing with uncertainties, including processing uncertainty. If you know that you need to review processing uncertainty and it's going to take a lot of time to do that, I probably wouldn't prioritize that for the midterm. I'd prioritize it for our next data collecting and processing lab. And then we also had vector addition and subtraction. The only thing I'll point out there is remember if we are adding two vectors, whether they're perpendicular or not, we have to sketch the second one starting at the tip of the first one, right? And then the resultant goes from the tail of the first to the head of the last. Never, never, never add vectors tail to tail. That's terrible, right? Tip to tail, head to tail. All right, topic 2 was our biggest topic of the semester, and I think of the year. Topic 8 comes close. And that came in 4 different subparts, right? Kinematics, which is just our acceleration, velocity, right? Motion. We have forces and dynamics, work, energy, and power, and then circular motion. So in kinematics, right, we did have a number of different equations of uniformly accelerated motion. That's all of our equations with acceleration in them. Remember, they only work if we have a constant acceleration, a uniform acceleration. Our very first equation last year was an equation for average velocity, and that it's the displacement over the time interval. You better be careful using that equation, because this is only good for average velocity. If we have acceleration, right, then you need to be very careful about what you use for that average velocity. If we don't have acceleration, then whatever, right? The velocity is constant. Use it, no problem. If the velocity is changing, be darn careful about using that equation. If it's changing at a constant rate, so if the acceleration is uniform, then yes, you're allowed to add the initial and final velocity together and divide by 2, but I continued this year to see some problems with that. Air resistance, really all we need to know is that air resistance slows down motion. We had all of our different motion graphs, position versus time, displacement versus time, velocity versus time, speed versus time, acceleration versus time, right? We're pretty good with showing motions on those things and interpreting motions on those things. Make sure you're also good about knowing what the slopes of those things represent and the areas under the curves represent. We do have essential questions for all of them, so that would be a good place to look over the weekend once I've corrected all of your responses. The next section was forces and dynamics. So remember that we did have a very slight change this year when we drew free body diagrams. Right? If I have a bicycle, bicycle looks like, whatever. Close enough. The only difference we had this year is we start our forces at, oops, that's wrong. We start our forces at the location where that force is exerted. So if I want to show the normal force acting on this bicycle, I want to do 2 of them, right? Because the ground actually pushes up both here and here. So I want to do both of them. The weight, though, we generally start at the center of mass, because the Earth is kind of treating this thing like all the mass is at the center, so that one we can start at the center. We had all of Newton's laws. We want to know which is which, and remember that in paper 2 questions, we're often asked to use Newton's laws to help describe things. Translational equilibrium was just a fancy term for when the net force was equal to 0, so we can have that if an object is motionless and stays motionless, or we can have it with a constant velocity. Constant non-zero velocity. We had our impulse momentum theorem here. All right, so that's certainly worth reviewing. The next subtopic was on work, energy, and power. So we reviewed that work is force times displacement times the cosine of the angle between those two things. We reviewed that energy is always conserved, but mechanical energy is not always conserved. Anytime that we're creating a non-mechanical form of energy like heat, then mechanical energy wouldn't be conserved. And then we did see our elastic and inelastic collisions. What is our only conclusive piece of evidence for an elastic collision? What, Ethan?
Oh, no, sorry.
What is the only way we can definitively tell if we had an elastic collision? No, that's perfectly inelastic. They stick together. Something gets conserved. Kinetic energy stays constant with an elastic collision. That's the only way to tell for sure that a collision was elastic. And then the last piece of topic 2 was our circular motion. So at this point, the direction of centripetal acceleration, centripetal force, and circular velocity should be second nature to you. If we have something moving in a circle, right, the acceleration vector and the force vector always point in towards the center of the circle. Let me rephrase that. If we're moving at a constant speed around the circle, then they point perfectly inward. Whereas the velocity vector is perpendicular to that, tangent to the circle. It's very normal to have questions where we're looking for the agent of that centripetal force. Sometimes it's a gravitational force, like the moon's orbit. Sometimes it's a frictional force, like a car rounding a curve. Sometimes it's a tension force if something's tied to a string. But we definitely want to recognize that centripetal is not an agent. Something has to be providing that centripetal force. Other issues from you guys with topic 2? Okay, topic 3 was on our thermal physics, and we had 2 subtopics. First was called thermal concepts, and then the second was called thermal properties of matter. So the biggest, most important thermal concept was that if we have 2 objects that are exchanging thermal energy, the only thing that impacts the direction of the net thermal energy transfer is the temperature of the 2 objects. If they're at the same temperature, then there should be no net exchange of thermal energy. Why do you guys scribble all this? I posted this why would you be frantically writing this all? It makes no sense to me. So whatever. So that's the most important. We learned about internal energy for the first time. It is different from thermal energy. Thermal energy is energy that is transferred from one thing to another. Internal energy is that energy inside of objects. It is both the potential energy of the molecules of the substance and their kinetic energy, whether it's vibrational or translational or rotational, right? But for most solids, this is mostly in the form of vibrational kinetic energy, that jiggling that we kept talking about in topic 3. And then finally, we had our thermal properties of matter. So we learned about specific heat capacity as well as thermal capacity. That involved, energy going to cause a temperature change, right? And specific heat capacity factors out mass. Whereas thermal capacity, which I never remember if it has a symbol or not, thermal capacity does not include mass, right? So we could take, I don't know, right? Liam's pretty big, a lot bigger than me, right? So it would take more energy to change his body by the same temperature as mine. Right? He's bigger, so it takes more energy if we're going to heat him up more than we're going to heat me up. Even though we probably have the same specific heat capacity, we have different thermal capacities because of our different sizes. So specific heat capacity factors out that mass term. We looked at the difference between our 3 normal states of matter, solids, liquids, and gases. We looked at those differences in terms of the structure of the molecules, but also the behavior of the molecules. We looked at phase changes, right? We had these heating and cooling diagrams where we tracked the temperature of something as a function of time. Let me get this right. That's almost right. That's pretty good. So we have these heating diagrams where we have these flat sections. where even if we add energy, the temperature doesn't change. Those are our phase changes. And then we had the linear sections where the temperature does change. That's where we have a solid here. As soon as we reach the melting temperature, right, we start changing from a solid to a liquid. And as we're delivering that energy, the temperature stays constant because all of that energy is going to increase the potential energy of the molecules, not the kinetic energy. We did talk about evaporation. We watched that water evaporate for like 2.5 months until it finally left, right? So hopefully we actually have a better sense of evaporation now than we did when we first learned about that. Right? Different states of matter, solid, liquid, gas, have different values for their specific heat capacities, right? So ice and liquid water, we don't use the same value. And then I think, we actually didn't review this. I would say this might be equally the most important thing from this topic with the temperature determining the net thermal energy transfer. Temperature also, right, is giving us a measure of that average molecular kinetic energy. All right, so those are the things that really jumped out at me as being either important or at least review worthy. Other questions from you guys about topic 3 stuff? Okay. So I don't know how much more time we have. I have about 90 seconds more stuff that I'd like to talk about. And that relates to our second objective from today, which was the direction of a force on our moving charge. So we use this right-hand rule. Right, so let's see, let's do one. So we have a magnetic field that points that way, so point your hand that way. Do it. Let's have the positive charge moving towards the front of the room, so put your thumb towards the front of the room. And this right-hand rule tells us that the charge gets forced down. What is the charge going to do in response to that force? Starts with A. Accelerate. And its direction will change. And guess what we have to do when its direction changes? We have to change the direction our thumb points, right? So as the thing accelerates, right, the direction of the force changes as well. So when we have a charge moving through a magnetic field, we're not going to have a kink. Right? We're not going to have a single change in direction. We're going to have a continuous change of direction. Maybe we'll actually have some uniform circular motion due to that. In fact, I have a very, very, very short video clip that does a better job than that diagram of showing that to us. So let's real quick look at that. Right? But this is a really important thing. We don't get into, so here we have a magnetic field that points up. We have a positive charge that was mostly moving perpendicular to the field, but must have had a small component of its velocity in the same direction. All right, so I'll see you guys Friday. Make sure that you get your essential questions answered if they're not answered already.
You go to lunch now, right?
Yes, you go to lunch now.
Should we put the